Good morning, everybody. Y'all doing okay? Listen, our exam is on Wednesday, okay? And don't forget, you do have a quiz that's coming up on tonight. Actually, it's due tonight at midnight. You have your reading assignment and the... What? Oh, I thought there was a perfect. Is that everything okay? Yeah, so the quiz is due tonight at midnight. There's a reading assignment too. Listen, don't forget, I sent out the answer to number 3. I think it was like 85 or something. Is that right? What I sent out. So that's not the right answer. In fact, it's not even a question that I would ask. I'm sorry, it wasn't really something that I would look that closely at, obviously. And also for number 4, I've had a number of y'all ask me about number 4, the one with the tornado that goes around. And a lot of you are having trouble with that. But I want you to, before you think that you're doing it wrong, look at the units, because the units in number 4 are given in revolutions per second, but you're probably calculating something in radians per second. So think about your units. If you have trouble with that, let me know, okay? Y'all have any issues or whatever to bring up? Today we're going to review for the exam, and I have to actually let you out at 10:28. Is that okay? I have a meeting. 11:28, yes. 11:28. Okay? So let's get started. I'm going to review all the topics that we'll have. Oh, and then also don't forget there is another review session at noon in Beauregard 210 on Tuesday. That's one of these rooms upstairs. If you can make it, that's great. If not, that's okay too, but I'll try to record it and post it on YouTube. So this test covers chapters 5, 6, 7, and then you'll have 2 or 3 problems from chapter 8. So sort of chapter 8, but I'm going to tell you exactly the types of problems. I've already told you, but I'll look at them again today. So in chapter 5 is probably the biggest part of your exam, although they're all pretty much equally weighted. This is energy and work. So you need to know how to calculate the work. That is, this work equals FD cosine theta jazz. Just be able to calculate if you have a force over a displacement, be able to calculate the work. You also need to know the work energy theorem. That is that if you do work on an object, you change its energy. Like for example, if I have a force that acts over a displacement, then that can give an object kinetic energy. And we worked through some problems where I actually calculated what was the speed of the object after this force has acted on this object over a certain displacement. So that's the work energy theorem. Then you need to understand the positive, negative aspects of work. If the force and displacement are in the same direction, that's positive. If they're in opposite directions, that's negative. You need to know kinetic energy and potential energy. And particularly, you need to know the conservation of energy. Listen, you'll have one of these questions where you have a little roller coaster and you have to figure out what is the speed or the height at particular points. We've worked through several of those examples, and if you look back at the old tests, they're on all the old tests. So make sure that you can do that. The key here is figuring out what I have at each point. Do I have potential, kinetic, or both? Ask yourself, is the height 0? If it is 0, then the potential is 0. Ask yourself, is the speed 0? If it is 0, then the kinetic energy is 0. But the sum of those energies will always be the same. It always remains constant, and it'll always be the same at every point along your system. You also might see a conservation of energy problem dealing with springs. We worked through some of these like this. Remember, it works out exactly the same, but my potential energy for the spring is 1/2 kx squared. And so, for example, we worked through a problem in class where if I compress the spring by a certain amount and then let it go, I can calculate the speed of this block because all of that elastic potential energy is converted into kinetic energy. So conservation of energy as it relates to gravitational energy and to elastic potential energy and kinetic energy too, of course. Kinetic energy. We had Hooke's law. I don't even remember if this is on here. You just need, if you have a spring that is compressed a certain distance, you should know how to calculate the force. This equation is on your equation sheet, which you'll have on the test. So just know that if you have something like that, that's how you calculate it. And then likewise, something that's less important is the whole issue of power is work over time. We had a couple of questions on the concept test, and you might have a calculation, but maybe, maybe not. But sorry, I don't remember if I put it on there. I don't think I did, but I'm not certain that I didn't. Is that clear? Might be on there. I'm not sure. But it's the work over time. If you do a certain amount of work in a certain amount of time, you just divide the two to get the amount of power. Remember, that's in watts, or joules per second. That's chapter 5. Then chapter 6 is momentum. We can come back if, oh, Olivia, yeah. Yeah, it could either be work or energy over time. Yes, yes, that's okay. It could be potential work.
Because there was one problem where instead of work, it was actually the kinetic energy.
Yes, you can do that. So when we think about work and energy, we sort of interchange those two variables. So it could be energy over time as well. Okay? Chapter 6, you have two classes of problems. You have the impulse problems, that is F equals delta P over delta T. And then you also have the collision problems. That is that PI equals PF. These are all vector quantities except for time. You can tell these differently because, first of all, if I'm asking a question for the force, then you're going to use this because, you know, you're finding the force, and this doesn't have a force involved in it. You'll also see that this will only involve one body that collides with something that doesn't move. So like something run into a wall or just something that doesn't move. Like, for example, the football player catches the football. He doesn't move, but the football does move. So you'll be able to tell those because, one, it has a force involved, or asking for a force, and two, it only has one body that moves. The collision problems, on the other hand, will have two bodies that are moving, and you have to figure out what is the final velocity of one of those bodies. Also, in those collisions, you need to know elastic versus inelastic. Remember, elastic conserve energy and momentum. And inelastic conserve only momentum. In fact, every collision that has ever occurred or that will ever occur conserves momentum, but only a very select few conserve energy too. Anytime you have two things that come into contact, when they collide, they do not conserve energy. They lose a little bit of energy. So elastic collisions include really just, you know, charged particles because they collide, but they don't touch because they're charged. Need to know about the vector nature of momentum. We talked about how that we can have objects that are moving that have zero momentum because they have momentum vectors that are equal and opposite. That's it for chapter 7, or chapter 6 rather. Chapter 7 is on rotational kinematics. You need to know how to convert, or you need to know your kinematics equations. That is omega equals omega naught plus alpha t. Actually, you don't need to know them, but you need to know how to apply them because you'll have them on your equation sheet. And so as you work through problems, you need to be able to read the problems and figure out what it is that you know. Write that down, like, you know, I know omega, and I know omega naught, and I know alpha, and then figure out what is it that you don't know. I need to find the time or whatever. Some of the quiz questions that you have to do tonight are good examples of test questions. In fact, I did pull, gosh, I don't know, 5 or 6 or maybe even 7 questions from the OpenStax quizzes, and they're pretty much verbatim from, you know, all 4 that we've had for these chapters, 1 or 2 from each chapter. So I would go back and review those as well, the OpenStax quizzes. If you have any questions about them, if you can send me an email or come by and see me. If you send me an email, shoot me a screenshot of the question and whatever you have. Okay? All right, so know these kinematics. Also, you need to know how to relate your angular to linear quantities. So that was where we had this S equals theta R, V equals omega R, and A equals alpha R. Actually, the tornado question, you had to do something like this, but you had to be careful with your units and how you're dealt with that. No directions. Remember we did that right-hand rule business with the fingers? Don't worry about that. That's just sort of thrown in because we're going to see it again later. And then centripetal forces. You need to know about the nature of centripetal forces. They're center-seeking. They're always towards the center of the circle. You need to know how to sometimes different forces act as centripetal forces. We talked about 3 different examples in class. So, like for example, the ball on a string, the tension was the centripetal force. If I have the gravitron thing, like the fair ride, the normal force provides the wall pushes up against you and pushes you into this circular path. And then what was the other one? Oh, the car on the road, the frictional force provides the centripetal force. Any force that makes you go into a circular path, that is the centripetal force. We can calculate the centripetal force in a couple of different ways. We say Fc is mv squared over r. Or if you don't know v, then you can say Fc equals m omega squared r. All we did is we just took this and plugged it in for v. So those are both on your equation sheet. Be able to calculate the centripetal force and or the centripetal acceleration. Those are related, right? The centripetal force is the mass times the acceleration, ma, Newton's second law. And the centripetal acceleration is this v squared over r. All right, that's chapter 7. Yeah. That's true. Yes. Okay, don't hear what she said. She said the statement she said was true, that if your normal force, if you're on an inclined plane, the normal force is not equal to your weight, it's something less than your weight, right? If you're on a flat surface, the normal force is equal to your weight. That's what you said, right? Okay. All right. That did come up on some of your quizzes, like I think in the energy quiz, if I'm not mistaken. All right, make sure you look through your homework. There are some good problems in your homework, though I understand in Chapter 7 there was one question, I think just one, that required you to substitute one equation into the other. You had 2 equations and 2 unknowns. You won't see that type of algebra on the exam. All right, the algebra I think on this exam is probably a little bit stepped down from the previous exam. It is a little bit stepped down from the previous exam. So not easier, just, you know, less substitution type problems. Okay, and then in chapter 8 you had 3 types of problems. I went over these in class last time, but let me just review them. You're going to have one where you have to find the net torque. I'm going to give you an object like this. It'll be a bar. It'll be rotating about some axis. Say it'll be rotating about this axis. And it'll have 3 forces acting upon it. A force here, and maybe a force here. I'll give you those forces, say 10 newtons, 20 newtons, 5 newtons, and I'll give you the angles, 30 degrees, 40 degrees. And you have to figure out what is the net torque. Remember, on these you need to go through and first figure out which ones do 0 torque. On this one, there's only one that does 0. It's this one, because R is equal to 0, so the torque given by that force is 0. So I can just forget about it completely. And then the other 2, you'd also know the distances. So like we did in class, say this is 4 meters, this is 2 meters. And then you would figure out which torques are positive and which are negative. This force causes clockwise motion. This force causes counterclockwise motion. So this torque is negative and this torque is positive. Right, so figure out what your positive and negative torques and then calculate your torques. Torque equals Fr sine theta. So for example here, it would be 10 times 2 times sine of 90, which is 1. Here it would be 5 times 2, which is the distance from where the force is applied to the axis of rotation. Your axis of rotation will not be in the center, I'm fairly certain. So make sure that you're clear on where that axis of rotation is and how to measure what your R value is. It's from the axis of rotation to where the force is applied. And then times the sine of 30. Now, one of the examples we did in class, I measured the angle from the y-axis, but it'll be measured from the x-axis, so you don't need to sweat that. Just take the angle that I give you. The second type will be just like you did in the lab. I'll give you some system. There will be some force over here. Say this force is 2 newtons at 5 meters. And I want to know, where does the force, say, equal to 5 newtons? Where would that force go in order for this thing to be balanced? So you say this force times whatever distance it is equal to this force times this distance. That would mean that your torques are balanced. So the torque on the left-hand side would equal the torque on the right-hand side. So I would say 5 newtons times R is equal to 2 newtons times 5 meters. And so R would equal to 2 meters. So this 5 Newton force would go right about here at 2 meters. And that would be your answer. So you'll have one of those, an equilibrium problem, where you have the torques balanced, and you have to figure out where that is. Just like we did in lab, exactly like that. No, except we'll only have one force on one side and one force on the other side. Nothing hinky like we did in lab with the center of mass and all that business. We'll get more into this in the next exam, but I just want to go ahead and throw this out here. And then, like we did in class last time, this may or may not make the exam. Right now it's on there, but I might take it off. Is I'll give you a series of problems where you have forces acting on different objects, and you have to rank the torques, just like we did in the concept tests. Those concept tests are uploaded now to the website, including actually Chapter 7 is up in its entirety. So we're going to see Chapter 7 again, but if you want to go ahead and print those out, you can have them for, just bring them to class or whatever. Y'all understand what I'm saying? Like the answers for the clicker questions are on the website now, for the ones we'll do in the next chapter. Okay? That's it for 5, 6, 7, and then this is just a little bit of 8. If you look at the old exams, you'll find some like this, and you'll find them. They're there, these questions, but this is only a small portion of Chapter 8, so in every exam you might not find these questions. Okay? Are there particular areas where you feel uncertain?
Okay. There's a homework problem number 2 that we did together. Can you explain why we use those two?
For part A, right? Why do we use this one?
Yeah, why we use these two?
Okay. Yeah, so this was homework problem number for Chapter 8. It was number 2. So I'm not going to pull it up. I'll draw the figure, but it's, I don't know what page it's on either. But we had a bar like this, and in part A, it was rotating about this point, and then we had 3 forces acting on it, here, here, and here. And Maggie asked, why did we use these forces, here and here? And the reason we didn't use this force is because R is equal to 0 for that force. And since R is equal to 0, that means the torque is equal to 0. I'm glad you asked that question, because students often mess this up, okay? Your torque can be equal to 0 for 2 reasons. One, that you're pushing at the axis of rotation, and that's the reason here, that R is equal to 0. The other reason that your torque could be 0 is, so let's say that we had a force right here. In this case, my angle is 180, and the sine of 180 is 0. So 2 reasons that your torque can be 0 is if you're pushing at the axis of rotation right here, you don't get any torque, or if you push along the axis. So if I push sort of on this axis on that hinge. Did that answer your question?
So if it was in the middle, then
Yeah.
you use since you have this on.
Right, if your axis of rotation as you go on in that problem, it changes to this point, then you use these two forces and this one doesn't provide any torque at all.
But whatever that axis of rotation.
The axis of rotation is very important. All right.
Can you explain again by looking at the picture, just how to determine which direction the torque is going at this point?
Sure. I like to use a pen or a pencil. She asks, how do you determine the direction of the torque? So let's say it's rotating about this axis. This force pulls up. See how it pulls up in this direction? And so that force all by itself would cause it to move in that direction. Let's see, that is, what is that? That's counterclockwise, right? This force over here, it pulls down. It's only a component actually that pulls down, but it does pull down. And so this force down at the end, all by itself, would cause clockwise motion. That's right. That's another thing that students have trouble with those problems, is figuring out when the torque is zero and the direction of the torque. Imagine now instead it was rotating around this axis. They're going to change now. Well, first of all, this doesn't cause any torque at all. This one now causes clockwise torque, that one down there, and this force causes counterclockwise torque, that force down there. I like to use my pencil on my test. I mean, I do take a test, but you know. But I still use my pencil because I can never remember. There's no surefire way to remember it. Like some of you can just see it in your head, but not me. Okay? These are all good questions. Yeah. Sure. So let's just pull up our equation sheet. Which you will have on your exam. So can I write on this? So we're looking at chapter 7. These are all of our equations that we have. Remember, you can sort of make them out, that what we had for x is now theta. Theta is a measure of your angular position. The SI unit is in radians, though sometimes you see it in revolutions or degrees. And remember, as I said, you can never go wrong converting it to radians, but especially on this test, it's not really going to matter that much. You'll often be able to leave it in degrees or revolutions. But you need to just be careful and look at your units and look at the problem and figure out, if you have any doubt, just convert everything to radians. Okay? Remember, with that conversion, and I'm pretty sure you have a problem of converting, say, radians to degrees or to revolutions, that 2 pi radians is equal to 360 degrees is equal to 1 revolution. And hey, I've had about 3 people in my office this morning that have all made the same mistake in their calculators. Look, if you want to convert, say, 3 radians to degrees, then what you want to do is you multiply, or you divide it by 2 pi radians, and there are 360 degrees in that. When you do this in your calculator, you have to be careful that you do 3 divided by 2 pi with parentheses, because if you don't put in these parentheses, you know what you get? You get 1.5 pi. If you leave out the parentheses, and then you'll get the answer wrong. You'll do that scratching your head. I'm not going to give that as a misleading answer, but it'll cause you a lot of confusion. Y'all clear on that? Just make sure your order of operations are good. Yeah, MS. It's going to be 25 to 27 questions. It's about the same as previous, 25, I don't know. Right now it's 27, but I usually take out a few questions. Okay? So anyway, x is theta. V is now omega. And A is now alpha. That's our position, our angular position, velocity, and acceleration. Radians, radians per second squared. Now t is, of course, time. This is how we convert our linear to our angular quantities and vice versa. Brendan, what's that? The S, I wrote it as S, it's sort of like X. But I write it as S because that's what's used in geometry for your arc, right? The distance over an arc, we usually use S for that. Okay? Yeah, same as before. Although, just a second, I'm looking at. I don't want to, like, lead you into, like, I don't know, this false sense of security, but the kinematics problems will be less complicated than they were on chapter 2. Because in chapter 2, you had to substitute, or you had to find this or that, find this or that. The kinematics problems, of which there are 2 or 3, will be more one-step type problems. Kind of like on the quiz. Several of those were one-step problems. Olivia? Is that the substitution part? Was that the drill? Yeah, you could see one like that. It deals with centripetal force. We worked one like that in class, where you had the truck going around the curve, and you had to figure out what's its maximum speed. Now, I would probably make it a little simpler with that. For that one, you had to figure out first what was mu, and then you had to figure out what was v and uv. I would probably ask you, what is the maximum safe speed on this road if the coefficient of kinetic friction is whatever? Okay? There was a simple way to work out where you just take ratios, but you can't do that in class. Okay? What else, Bill? I can scroll through some, yeah, later. Yeah, let's see, where does that come up? Like in collisions or in energy form? Did you have that? You could have that. Conservative forces versus non-conservative forces. I don't remember if I put that on there. But conservative forces conserve energy. Anytime we talk about conservative things in physics, it's usually referring to energy. Conservative forces conserve energy. Non-conservative forces don't conserve energy. That means they lose energy. Like friction is a non-conservative force because as friction acts over a distance, that object will lose energy, right? It slows down, it loses energy. So, yeah, you need to know conservative versus non-conservative. A good example of a conservative force is a field force. In fact, those are the only conservative forces. Gravity and electric forces are conservative. Your nuclear field forces are conservative too, but just know gravity and electric field forces. You also need to know elastic versus inelastic collisions. I mentioned this earlier, but elastic, they conserve energy and momentum. Inelastic only conserve momentum. You could have a perfectly inelastic. I consider that to really just be a special case. Remember with perfectly inelastic, you don't even know what it's called, but you need to know what to do when 2 objects stick together. Huh? You add their masses. Yeah, so they work just like our regular 2-body collisions, except they're a little bit simpler because you only have one term in the final state because the 2 masses move off at the same velocity. I think that you have a collision that's perfectly inelastic. Pretty sure you do. But you need to know how to do both. William? Uh-huh. Oh yeah, so yeah, you also need to do times for 360. But I was just saying, in your calculator, when you do this divided by 2 pi, I just say this because I've seen about 3 or 4 people do this mistake, that you put that 2 pi in parentheses, or you just put, 6.28 as the number. Okay? Yeah, 13 minutes. Tell me. Yeah, which one? What was the number again? I would recommend that you work through these old exams and practice with them, that you work through them without any help at first and just see how you do, and then go back and see which ones you missed. Or if you didn't miss any, then move on to the next one and continue practicing in that way. Also, don't forget your OpenStax quizzes are good practice for you because I pull questions straight from there. And then the homework, too, is a good place to go. All right, so I have a 40-kilogram block. It's resting at a height of 5 meters off the ground. It's released and falls to the ground. Which of the following is closest to its total mechanical energy at a height of 2 meters? So this object is at 5 meters. And then I ask, at 2 meters, at a height of 2 meters, what is its total energy? Now, you could do this the hard way or you could do it the easy way. And the easy way is to say that the total amount of energy that it has here is the same as the total energy that it has here, right? The total energy that it has here is M times G times H. So it's 40 times 10, which is G. That's 400 times 5, which is 2,000. So C is the right answer. It has 2,000 joules here. And because of the conservation of energy, it also has 2,000 joules here. Now you also need to know how to calculate the velocity at that point, or what is the speed of the object. And you would say mgh, that's the potential energy at the top, is equal to mgh, where this is 5, this is 2, plus 1/2 mv squared. That's not what this problem is asking, but you need to know how to work those type problems as well. That answer your question? I said that the total amount of energy that the object has up here is equal to the mass, is all potential energy. The mass times gravity times h, that's 40 kilograms, times 10, times 5 meters, and that's 2,000 joules. Alrighty. What else, folks? I can just scroll through these, but you be thinking, this is Fall 14. It's a good one to go to because it only has chapters 5 and 6. I can clear this away. Some work problems there. Make sure you understand if you increase the speed, what does that do to the kinetic energy? If you increase the height, our concept tests, which are on the website, have that. Make sure you understand the whole thing about work doing positive and forces doing positive and negative work. You'll have a problem like this. You'll have a problem involving springs and the energy of springs. Pretty sure you have this is a momentum problem, number 17, where you calculate the change in momentum over time to find the force. Collision problem. Anything standing out that you want me to work through? Sure. Okay, so the spring, I have this spring that's compressed here. It's compressed by 10 centimeters. So that's my x value, which is, I want to convert that into meters. So it's 0.1 meters. And then I want to know the velocity of it after it leaves the spring. So it has potential energy here of the spring, and it's going to be all converted into kinetic energy. It's like a spring-loaded gun. You shoot off this mass, and it goes off into space at a certain velocity or certain speed. And so the potential energy is 1/2 kx squared equals 1/2 mv squared. See, I'll just get rid of those halves. K is given. It's 100 times 0.1 squared equals to 2 kilograms times v squared. And then I solve for v. So 100, 1 over 10 squared is this is 1 divided by 2 equals v squared, square root of both sides. What's the square root of 2? I mean, the square root of 0.5. 0.7? Is that right, the answer? Just a second, China. It was about this question? Okay, let's look. The 0.1 Oh, so be careful with your springs because nobody composes a spring by a meter, not very often. So just check your units. It was compressed by 10 centimeters, and 10 centimeters is 0.1 meters. Centimeters to meters, you just move it over twice, okay? Because there are 100 centimeters in a meter. Okay? You can see different variations of this. Like, what if, for example, I have a mass at, say, 5 meters, and it has a mass of, say, 2 kilograms, and I drop it down onto a spring with a spring constant equal to 100. How much does it compress the spring? This would be a very similar question. You would say the potential energy of the block, the gravitational potential energy, will all go into potential energy of the spring. All right, whatever energy the block has here is going to go into the spring when it compresses that spring. And so you'd say mgh equals 1/2 kx squared. And then in this case, you would solve for x, finding how much it compresses. That would be 2 times 10 times 5. That's 100. Equals 1/2 of 100. That's 50. X squared. X is 1.4. Square root of 2 is 1.4, I think. Okay? That's a similar problem, but a little bit different. So, a little bit different. Okay. Olivia?
It's just, it's on everybody's page. But are we supposed to say that? Or is he just saying this was done in zero? Is that something looking at? Looking at the energy so that's how he is. But then we have
So she's pointing to a figure that we had in our notes where we had a spring all compressed up. This is its equilibrium position, x equals 0. And I said that the potential energy of the spring is 1/2 kx squared, and the kinetic energy was equal to 0. That's true. This object, where is it? This object, which isn't moving, has no kinetic energy. So Ke equals 0. However, the spring is all compressed up, so it's holding a lot of energy. And that energy is equal to 1/2 kx squared. Now those aren't equal, the potential and kinetic energy, but the sum of them gives the total amount of energy. So no, that shouldn't be taken as a place to say that this is equal to this necessarily in that case, because obviously here the potential and kinetic aren't 0. But over here we have all the potential energy at this point. When the block gets to this point where there is no potential energy, it only has kinetic energy. So we say the potential energy is initially this. It's all converted into kinetic energy. They're not always equal, though. It depends where you are. Okay? What's that? Okay. All right. Tomorrow at noon we'll have a health session. I feel okay about this exam. I think we okay with it. We're doing okay, sorta, kinda. Sort of. I think sorta, not kinda. Listen, I'll be around after lab at 10:20 tomorrow. If you need extra help, please proceed. If you have any questions, let me know. Okay.